only bring this up to prove that angular vectors exist. They're just really limited because you can only ever spin forwards or backwards. But technically it's still a vector in that there would be a positive or a negative sign, so you do need to be aware of it. The direction still matters here, but it's only going to be positive forwards, negative backwards. Yes?
When you say forwards and backwards, is that referring to like just the wheel, or does that also include like a ball, sphere?
Anything that rotates. I mean, you, just like you would have to pick, whether left or right, up or down is positive or negative, you'll also have to choose whether clockwise or counterclockwise is positive or negative. Zoom tight. And now let's use this a little bit. Quick example, very quick example. A car is driving forwards, and as this car accelerates, its wheels will also be accelerating angularly. The wheels are spinning. They're going to be spinning at a different rate as the car linearly accelerates. Now, this car begins at an initial velocity of 29 meters per second, and then it begins slowing down. We do know the magnitude of its deceleration linearly. I'm just going to go ahead and start listing variables. Velocity initial is 29 meters per second. It's slowing to a stop, so velocity final is 0 meters per second. And the acceleration is negative, it is slowing down, negative 1.75 meters per second squared. The car is still moving forwards, it's just getting slower. We do not know the distance forward that the car moves during this time, and we don't know how long this process takes to get from here to here. But we do know the radius of the car's tires, part A tells us that. And the question asks us, how many revolutions does each tire make before the car comes to a complete stop? We want to know the number of revolutions for each tire on this vehicle over this process. Now, we know a lot of linear information about this car because we were able to examine it on the car as it was just moving forwards. We eventually want to know angular information. And so there's two paths you could take with this. And I'm going to let you guys choose which path we take. From the same starting point, with all the information that we know, we could go one way where we convert to angular, then solve. And that'll get us to our answer. Or the other way, we could solve in linear and then convert to angular. So we can examine the linear motion of the vehicle and then extrapolate the angular information. Or we can find the angular information and solve for this within the angular space. They will both get us to exactly the same point. The question is just, which one do you think we should start with? Where should we begin? Gesundheit. Now, if no one has any opinions, we have begun with a lot of linear information. And so, if we solve linearly and then convert our answer to angular, that's less conversions than if we convert all this to angular and then solve it angularly. So, based on the fact we have a lot of linear information, my vote is for us to solve it in linear and then convert it to angular. Does everyone concur? Okay. But either method works, and sometimes you might need to vary it a little bit based on just what information you have. You might start with a lot of angular information, and then it would make sense to keep it that way. Just depends on the question. So, in order to figure out the revolutions of the tires, we need to know the radians that the tires spin, and to find that from our linear information, we need to know how far forwards the truck moves, because we are able to convert linear displacement into angular displacement with the radius of the tires. So we want to find this, so we can find this, so we can find this, in that order. So, what we know is the initial velocity of the truck, the final velocity of the truck, and its linear acceleration. What formula can we use to find displacement? And I will go ahead and put them back up on the board. So what's our best bet? Yep, that fourth formula that we don't use super often, but when we need it, it's really handy to have. So velocity final squared equals velocity initial squared plus 2a delta x. So let's start working that. So linearly speaking, our final velocity is going to be 0. The car is slowing down to a stop. Our initial velocity is 29. That's going to be squared. 2 times acceleration. We are slowing down, so you need to plug in a negative acceleration. The car is slowing down from this speed to this speed. And then we are solving for how far forward the truck moves in this time. Does everyone concur with this formula's setup? All right. Drag this to the other side. 2 times positive 1.75. By subtracting this to the other side, we have gotten rid of the negatives. I've forgotten the answer, so I need to look at the notes. Yeah, that's it. Does anyone have an answer yet? Yep, I'm just going to round that slightly to just cut it off. As long as you have about 240 meters, well done. That is how far forwards the truck moves as it is slowing down. That's actually very far. That's over 2 football fields. So this is not a very big rate of deceleration. I think this driver just took his foot off of the gas and is letting friction slow him down. I don't think he actually hit the brakes. But that is the linear displacement of the truck as it slides forward, as it is slowing down. So now with that information, how can we get to the information we want about the rotation of the tires? Convert, using what?
Delta x equals radius times theta.
Yep, delta x equals r theta. We know how far forward the truck moves, and we know the radius of the truck's tires. So theta should equal 240 over 0.33, and I'm really bad at remembering numbers. There we go. Does everyone concur with this arithmetic? All right, So keep in mind, the default units that you would get from this formula is radians, not degrees, not revolutions, but radians. One full rotation is 2 pi radians. So if we want revolutions for each tire, we need to convert radians to revolutions. 728 radians. 2 pi radians is equal to 1 revolution. So we're going to end up dividing by 2 pi, so we'll get a smaller number of full revolutions in this process. So how many revolutions do these tires make as the truck slows down?
$1,143.5.
No.
Oops.
Is it 116?
116.
Shit.
I think you might have put something into your calculator wrong. Did you do answer divided by 2 and then pi? Because then it would divide by 2 and then multiply by pi, because calculators are dumb.
I'll try it.
Yeah, do open parentheses, 2 pi, close parentheses. Yeah, so the number of revolutions should always be smaller than the number of full radians, because 1 revolution is always more radians. There's more than 1 radian in a revolution. So this number should always be smaller than this one. But that's the first part of the question. Good job. So again, and if we worked it the other way, if we converted to angular and then worked it angular, we would use exactly the same formula, just the angular counterpart. Angular final velocity would equal angular initial velocity plus 2 times angular acceleration times angular displacement. The logic, the way it all works, is still exactly the same, which is why we were able to solve it linearly and then convert. The logic is all exactly as you'd expect. Now, the second part, which we're just going to go through quickly, I just want you guys to conceptually think about it. What is the angular speed of the wheels when the car has traveled half of this total distance? So instead of looking from start to stop, we're looking at a point in the middle where we have traveled half this distance forwards. The tires are still spinning. How fast are they spinning in this case? So what can we do to get to that point? Okay. We know how far forwards we move, so we know what half of that is. We can look at the exact same formula. Instead of plugging in our final velocity of 0 and solving for the total distance, we can plug in half the distance and we can solve for our velocity at that point. So same formula, VF squared equals VI squared plus 2A delta X. We're now solving for VF. Same starting velocity, same deceleration, but now we're looking at a fictional point partway through this process. Everyone follow this logic so far? I know it's morning. I know everyone's feeling the Mondays, even though it's Tuesday. We're almost done with the algebra. So does everyone concur with this linear final velocity? So this would be the speed that the car is moving at this halfway point. This is how far fast forwards the car is moving at this point. We want to convert that to angular velocity. Linear velocity equals radius times angular. So how can we turn this into the angular version? Yep, just divide by radius. So this divided by 0.33. And that should give everyone omega equals about 62 and some spare change. And again, all of our angular units are going to be the same as our linear units, but swap meters for radians. So your units for angular velocity are radians per second. And this just tells you how fast the wheels are spinning at this fictional point in the middle. How's everyone doing besides sleepy?
Do you guys know this for one of the problems on the homework where it's like going in a circle?
Yes. All of chapter 7 is kind of like this.
I did on the chapter 6 one.
Oh. No.
I could just not know how to do it. Very, very possible.
There are a couple on there that do have.
Like the last one, wasn't it? Or 11.
Little things on here that go spinning.
There's like one. Again, I could just not know how to
Maybe
do
number
it.
6.
Very possible.
I don't remember.
There is one question in part 8 that does involve a rotating orbiting object. Sorry, there's one question in the chapter 6 homework that involves a rotating orbiting object, but you don't need these to work it, strictly speaking. You can do it with just the energy equations. It is a very strange question, though, I will admit. But you can work number 8 with just the energy equation so far. Energy and collisions. That said, if number 8 gives anyone trouble, please come by, because I admit this is a weird one. But I need to keep talking about chapter 7 for the moment. Okay. So any questions on these so far? I know we've been doing a lot of lecturing in algebra, just straight through the morning so far. Does anyone know? In addition to questions, does anyone need water or just a minute to think? All right. We're near the end of lecture, but go ahead and pause for a moment, and I'll end lecture by introducing the next thing we'll do most of the next time. So is it just a bad morning for physics, or is it just a bleh day in total?
It's not even both. Yeah.
It feels like morning for me. I don't know why.
It's because this is a cake.
This is the most I've ever understood anything that comes out of your mouth.
Really?
Say.
Yeah. Like
Okay, so you're not asking questions because you actually don't have any.
Let's
that
not
it?
get carried away.
Now I'm not
But-
speaking for everybody, but it's going all right.
I mean, I will still choose to interpret things positively.
I don't want to scream.
You don't want to what?
I don't want to scream. Like at the end of this lecture, I feel like I'm gonna be okay.
Okay,
Which is a positive. Because normally I leave a little irritated.
I'm sorry.
It's not you. It's physics.
I want to help you understand the physics, though.
You're doing a great job. I haven't failed it, actually, it's a lie, I have failed a few things, but it's not your fault.
No, you haven't.
Yes, I have. I wrote you a 36 on one of my homeworks. And you said
Oh.
you made a 36, and I said, I told you I made a 36, it's not a surprise.
Well, every homework after that's going to be a lot better. Okay, so the next thing I just want to talk about, we're not gonna worry about too much algebra right now because we just worked a couple problems back to back. But the next concepts that we're going to begin talking about are things that you have definitely heard of and definitely experienced in your actual life, and that I know for certain are going to affect most of your careers for all of you biology, chemistry type people. So, who has heard of centrifugal force? Okay. Got one raised hand and one person who said absolutely, so I'll take that as a sign. All right, a couple more hands. Sorry, can we rotate that just a little bit? Sorry. Okay, centrifugal force. You have all felt it, I guarantee it, because even if you don't drive, I assume you've all been in a motor vehicle at this point. So, who has been in a car? The car takes a pretty sharp turn, and let's just say for the sake of argument that the car turns left, the car is turning left, and you all feel as though something is pulling your body to the right. That makes sense? That sounds like a thing you've experienced?
Yeah.
All right. That sensation that you're feeling is centrifugal force. So as an object starts rotating, I keep misplacing my erasers. Like I said before, when an object, yes,
Was centrifugal force the same thing that they use to simulate like G-force, like pilots that are testing?
yes, actually. And again, for all of you biologists and chemists, it's the same principle that lets a centrifuge work. The machine, you put the test tubes in and it spins and sorts out the samples based on density. Okay, so the car is driving forwards as it makes a left turn. Like I said before, even though the object is not part of a big circle, this turning pattern is still some arc length of some fictional circle with radius r. So there is still circular motion involved. Get out of my way, whiteboard. There is still circular motion involved. So the car, the poorly drawn car from above, this is a bird's eye view, is originally moving forwards. Actually I should use a different color for that. The car is originally moving forwards, it begins turning, and by the end, it's going to be moving that way. You're familiar with, as you turn to the left, it kind of feels like your body is getting pulled to the right. Okay, so that sensation that you're feeling is the centrifugal force. What's happening there is, your body has inertia and momentum. That property of the matter inside of your body is saying, keep moving forwards. Your body doesn't care that the car is turning. Your body, your mass, wants to keep doing the same thing it was just doing forever. So your body wants to keep moving forwards. What happens is, your lower body is seat belted into the car, and there's friction between your body and the seat. So your lower body gets pulled to the left with the vehicle. But your upper body wants to keep moving forwards. So your upper body tries to keep moving forwards as your lower body gets pulled along with the car. So it feels like your upper body gets yanked outwards to the right because your body wants to keep moving that way until your lower body pulls you along with the rest of you. So that sensation you feel is the centrifugal force, and it's caused by your body's inertia wanting to keep moving forwards. And like I said, this is the same principle that you get in a centrifuge. When you put the test tubes in the machine and they start spinning, the different particles inside of the sample, their inertia wants to keep moving in a straight line, but the wall of the test tube won't let them. The wall of the tube keeps them in and forces them to keep moving in a circle. And that's why the particulates then push out as far as they can and separate themselves based on density. So same principle, it's why the device is named after this concept. Now, I introduced this first because I know you've all felt it, and so what I'm going to say next might be a little confusing, but centrifugal force doesn't exist. It's called the fictional force because it's not actually a force. It is a sensation that you feel. I'm not telling you that your memory is wrong. I'm not telling you that you feel something that isn't there. What I'm telling you is it's not actually a force. There is no force exerted on your body pushing you out of the circle as you turn. That feeling isn't really a force pulling you out of the circle. That feeling that you get when you are turning left is because you, the organism, are not one solid object, and you have nerve endings that register the sensation of things pushing inside of you. You are not a single object. You are a bunch of things stuck together and filled with blood. And each of those blood cells is a separate object inside of your body. So it's not just your body, your bones, your muscles that have inertia telling you keep moving forwards. Every single one of your blood cells also has inertia and wants to keep moving forwards. So your body, the vessel, gets pulled along with the car because of the seatbelt, but your blood cells keep wanting to move that way. So what you're feeling here is your blood cells pushing out against the edge of your body, against your skin, and your skin is exerting a force to keep them in and make them turn left. So what you are feeling is not actually something pulling you out of the circle. What you are feeling is just your blood pushing against the wall of your body. If you didn't have blood, you wouldn't notice this. And that is why the centrifugal force is technically fictional. There's no force being exerted to cause this. The only reason you feel this is because we have blood and nerve endings, and because of the weird way that we are not a single object and how the inertia of all of our individual components functions. This is a thing that you feel. It is a concept, and it is important to understand, but it is technically not a force, at least not the force that is making you move in a circle. So it only exists from your point of view as you are moving through the circle because of what you are feeling. It feels like you're being pulled out of the circle, but you're actually not. There is a force acting on you in this time, and that force is called the centripetal force. And subsequently, because there's a centripetal force, and force equals mass times acceleration, there is also a centripetal acceleration. Now, the centrifugal force feels like it's pulling you out of the circle. And to briefly talk vocab terms here, does anyone know what the root word century means? Center. So centripetal, centrifugal, they both begin with the word center. But then you get to the next part. Does anyone have any idea what fugal and pedal mean?
In and out.
In and out, yes. I'm familiar with fugal as fleeing and pedal as seeking. So the centrifugal force, the one that you feel, is the center fleeing force. That's the sensation you feel. It makes you feel like you're getting pulled out of the circle because your inertia is telling you keep moving forwards. The centripetal force is the force that is actually making you move in a circle. It's the force that is pulling you towards the center and making you move in a circular way. So this is the acceleration, and therefore the force, that actually exists. And this is what makes you move in a circle. To demonstrate, I have a hanging mass, a string, and PVC pipe. That's the term. Forgot my own device for a second there. I'm going to stand over here because that's where the camera's pointing. Okay, so this is just a hanging mass on a string, and I am going to create a situation where there is a centripetal force acting on this mass. And I'm going to double knot this real quick. Before I do this demonstration, does anyone have any questions so far? I know you're packing, I just want to show you this real quick. Okay, so for every object moving within a circular motion, for every object that is rotating or orbiting, some existing force has to cause you to move in a circle. If I were to just throw this object forwards normally, and there was no string here, what would this object do?
Forward and down.
It would just go forwards and down because of gravity. But because there's a string here, the string is going to exert some force, a tension through the string, that pulls this object towards this center fixed point. So when I throw this forwards, the tension in the string acts as a... That's pointless.
I'm glad that didn't happen when I threw it.
Alright, just to be safe, I'm going to throw it this way. The tension in the string acts as a center-seeking force that pulls this thing towards the center. And I'm really uncoordinated today. Because there is a force that pulls this object towards the center of a fictional circle, it begins to move in a circle. The tension in the string is acting as a centripetal force that is always pulling towards the middle. The combination of this inward force and the object's own inertia that tells it to go forward creates circular movement. And I'm not going to let it hit anyone.
You say that, but
See? I've done this before. I'm a trained professional. It has never flung off and hit anyone.
but has it flung off?
No.
Okay.
We will be examining this concept and the math that goes into it next time. Do begin your homework, though. Come with questions. Welcome. I hope you all have a wonderful day. Yes. Let me get my. I'll turn it on.